Hello students, today's topic is Introduction from Bridge Engineering. Let's begin with the basic definition. A bridge is a structure that provides passage over an obstacle, such as a road, river, canal, or railway, without interrupting the natural function of that obstacle. The bridge is usually used to carry traffic, either roadways, cars, buses, or railways, trains, across a gap. So, in simple terms, imagine you need to cross a river, but without touching the river or disturbing boats that move in it. That structure you build across it is what we call a bridge. Components of a bridge. We divide a bridge into two major parts. 1. Substructure. 2. Superstructure. Let's look at them one by one. 1. Substructure. This is the lower part of the bridge below the bearings and includes the parts that are in contact with the ground or water. Let's go through its components. 1. Foundation. It's the bottommost part of the bridge. Like our legs support our body, the foundation supports the entire bridge. 2. Abutment. Located at the ends of the bridge. It holds the ends of the bridge deck and transfers load to the ground. Think of it like the shoulder where the bridge rests. 3. Pier. These are intermediate supports between abutments, mainly used in longer bridges. Imagine pillars holding up a long bench. Those are piers. 4. Wing walls and return walls. These are side walls at the ends of the bridge. Purpose? To hold the soil of the embankment and guide the water flow. Without them, the soil would erode away. 5. Revetment. It is a sloped stone or masonry covering on the sides. It prevents erosion due to water flow, like protection for the riverbank. 6. Apron. A horizontal bed-level flooring, usually placed at the inlet and outlet of the bridge. Its job is to protect the foundation from scarring, washing away. 7. Approaches. These are the sections of the road that connect to the bridge. Without approaches, we can't reach the bridge from the road. B. Superstructure. This is the part of the bridge above the bearings. Basically, the portion you walk or drive on. Main components are 1. Bearings. These are mechanical components placed between the substructure and superstructure. They allow movement due to temperature, load, and transfer the load safely. 2. Decking. This includes the flooring and beams on which the vehicles move. Simply put, this is the actual road surface of the bridge. 3. Handrails. Provided on both sides of the deck, for safety of pedestrians and vehicles. 4. Girders or trusses. These are horizontal structural members that carry the deck, used in short-span bridges where heavy loads need to be carried. 5. Roadway. This is the actual path or pavement laid on the decking. It's where the vehicles move. Let's now understand how bridge loads are standardized in India as per the Indian Roads Congress, IRC. Topic: IRC loading, classification. When we design a bridge, we must predict the type of loads it will carry during its lifetime. Who decides this? IRC, Indian Roads Congress, the governing body that provides standard guidelines. IRC classifies vehicle loading into 4 main types. Number 1. IRC Class AA loading. Number 2. IRC Class A loading. Number 3. IRC Class B loading. Number 4. IRC Class 70R loading. 1. IRC Class AA loading. This is the heaviest category of loading, primarily based on military vehicle movement. Where is it used? National highways, state highways, industrial zones, important municipal areas. Important point to be noted. Even if a bridge is designed for Class A loading, we must still check for Class A loading, because in some cases, bending moment due to Class A may be higher due to load distribution. IRC Class AA. 2 vehicle types. Let's break it down into 2. A. Tracked vehicle. Total load, 70 tons. Load spread over 2 tracks. Track width, 850 mm. Track length, 3600 mm. Vehicle length, 7200 mm. Distance between tracks, 2900 mm. Minimum spacing between two such vehicles on a bridge, 90 meters. These are like military tanks or earth movers, very heavy and compact. B. Wheeled vehicle. Single axle vehicle, load is equal to 20 tons. Double axle vehicle, load is equal to 40 tons. Axle spacing, not more than 1200 millimeters. Maximum wheel load, 6.25 tons. These resemble heavy-duty trucks with rubber tires. 2. IRC Class A loading. This is the standard loading for all important roads. Designed for heavy commercial vehicles that run daily on Indian roads. Used in design of permanent bridges and culverts. Example, a regular bridge over a state highway would be checked under Class A loading. 3. IRC Class B loading. This is a lighter version of Class A loading. Load reduced by 40% compared to Class A. Used in temporary structures, such as timber bridges, temporary crossings. Remember this, Class B is equal to 60% of Class A. 4. IRC Class 70R loading. This is an alternative to Class AA loading. The letter R stands for revised. Considered where very heavy loading is expected. Vehicles are hypothetical, not real world, but theoretical for safe design. Types under 70R. Tracked vehicle. Similar to Class AA tracked vehicle, but differs in ground contact area. Wheeled vehicle. Has 7 axles. Total load, 100 tons. These are extreme cases, used for specialized roads like defense corridors, expressways, or industrial haul roads. Let's now move into how we select the type, location, and span of a bridge, and understand important hydraulic terms like scour, afflux, and freeboard. Topic: Selection of type of bridge. Before designing any bridge, we must gather preliminary data. This data helps us decide what kind of bridge to build and where to build it. Key factors in selecting the bridge type. 1. Length and width of bridge. Longer bridges need stronger structures and more piers. 2. Traffic volume and type. Heavy traffic? Then we need RCC or steel bridges. Light rural traffic? Culverts or slab bridges may be enough. 3. Nature of river and soil. Rocky beds need different foundations than sandy riverbeds. 4. Material and fund availability. If local stone or timber is available, we may reduce cost. 5. Construction time. Some bridges take months, some can be precast and installed faster. 6. Site features. Is the site hilly? Marshy? Flat? This affects machinery, labor access, and design. 7. Labor skill level. Can local workers build complex trusses? Or should we go for simple RCC? 8. Economic span length. We will learn this in a moment. It means choosing span length to minimize overall cost. 9. Hydraulic data. Like HFL, highest flood level, and LWL, lowest water level. 10. Climatic and environmental conditions. Freezing zones? High rainfall? That influences material choice. 11. Live load on the bridge. Based on IRC loading classes we studied before. 12. Appearance, aesthetics. For urban or tourist areas, the bridge should look good too. Scour. Now let's understand scour, a very important hydraulic concept. What is scour? Scour is the erosion of soil from the riverbed, especially near bridge piers or abutments. Happens when the velocity of water exceeds the safe limit for that soil. Note down the formula for maximum scour depth, which is given below. In formula where D is equal to maximum scour depth in meters, Q is equal to discharge in cubic meter per sec, F is equal to Lacey's silt factor, depends on soil, R is equal to constant, typically between 1.27 and 2.75. The most important point here is, as discharge increases, scour depth increases. Scour prevention measures. Dumped stones or concrete blocks on the bed. Pitching with stones on the riverbanks. Providing sufficient waterway width. Uniform stream flow, no sharp bends. Streamlined pier shapes to reduce turbulence. Afflux. Now, Afflux is the rise in water level due to obstruction by a bridge. What is afflux? Occurs when water backs up on the upstream side of a bridge. Causes water level to rise, just like what happens when you partially block a flowing pipe. Higher afflux is equal to higher velocity is equal to more cost for protective works. So, we must minimize afflux during bridge design. Span terminologies. Let's learn 3 important definitions. 1. Clear span. The open distance between two supports without considering their thickness. 2. Effective span. Center to center distance between adjacent supports. 3. Economic span. The span length at which cost of superstructure is equal to cost of substructure, chosen to minimize total bridge cost. Factors affecting economic span. Local material availability, labor availability, waterway features, site condition. Waterway. Waterway is equal to cross-sectional area for water to flow under the bridge. Linear waterway is equal to sum of all clear spans at HFL level. Flood levels. HFL means highest flood level, that is the maximum flood level ever recorded. LWL means lowest water level, that is the minimum level during the dry season. Freeboard. The vertical gap between HFL and the lowest part of the bridge deck provides a safety margin for unexpected water rise. Selection of ideal site for a bridge. Now suppose you are selecting a location to construct a bridge. These are the checklist points. 1. Easy connectivity on both sides. 2. Well-defined embankments. 3. Availability of manpower and materials. 4. Shortest crossing width. 5. Uniform water flow to avoid silting or scarring. 6. Good foundation soil. 7. Right angle crossing of the river. 8. Straight stream on both sides. 9. Economical construction. 10. Low maintenance cost. 11. Availability of power. 12. Transport and communication should be easily accessible. Alignment of bridge. Alignment is equal to centerline of the bridge. Factors for good alignment. Economically feasible. Avoids silting and scarring. Perpendicular to river flow, preferably. Avoid curves. Ensure straight approach roads. That's all, students. We'll meet you in the next important video. Until then, keep preparing. Thank you.